Hi. HARTRON was established in 1959 in the USSR. Until 1991, it was the largest developer and manufacturer of strategic missile control systems, spacecraft carrier rockets, and heavy-class spacecraft control systems in the USSR. In areas such as flight dynamics, precision guidance, missile targeting, the creation of digital control systems and software development was conducted at a world level. Among the most significant achievements, it should be noted the development of control systems for SS-18, SS-19 rockets, Zyklon, the Energia launch vehicle, capable of launching objects weighing more than 100 tons, heavy spacecraft, and a unique system of automatic docking for orbital objects, developed on several generations of Soviet orbital stations. Carrier rockets with control systems developed by HARTRON launched about 1,000 spacecraft into orbit, including the first artificial Earth satellite manufactured in Ukraine. Now HARTRON is a group of companies, one of which is developing relay protection and automation. I'll open the product catalog. In the case that I will consider, the L030 device is used. This is an IED that performs the functions of phase differential protection and backup protection. The set of backup protections for the device is limited: 2 zones of distance protection, 2 steps of zero-sequence current protection, and current cutoff. There is a function for backing up breaker failure and wreck losing. In general, the device has hybrid logic. The user cannot change most of the logic, but it is also possible to adapt the device using freely programmable logic. In our case, 2 parallel lines are equipped with the same set of protections. On each line, 2 terminals L030 and 7SA611 from Siemens are installed on each side. At the same time, the phase differential protection function was disabled on the first line due to a malfunction of the high-frequency channel. Information was received from the dispatcher about the trip of the second line with unsuccessful automatic wreck lose and the unilateral trip of the first line by distance protection function in the L030 device at substation A. Initially, we assumed a false operation of the device at substation A along the first line. Let's look at the recording from the general substation recorder at this substation. I removed the unnecessary channels. Here, there is only the voltage of the bus and the currents of 2 lines. On the first line, phase B is damaged, on the second, phase A. Here we see a trip from the side of substation A, here a wreck lose from the side of substation A, here a wreck lose from the side of substation B, and then a short circuit occurs again. Let's take a closer look. At substation A, the first line trip was a little earlier, with an approximate time of about 80 milliseconds. Let's look at the vector diagram. I'll add the voltage and current of phase B of the first line. It's like the power is being directed to the bus. Let's see what happens to phase A. And now the arrangement of current vectors from different lines is typical for a 2-phase short circuit. Let's add zero-sequence calculated channels. There is no zero-sequence voltage. There is a zero sequence current along the first line. Same on the second line. Let's add the negative sequence. For an unambiguous determination, the negative sequence current must lead the negative sequence voltage by approximately 90 degrees. The angle is not 90 degrees. It's still a mystery to me why the current increases only in one phase on each line. In theory, it should increase in both. Let's see how the devices saw what was happening. I'm adding 2 zones because this device doesn't have more. I enter the settings. The device uses only distance protection for phase-to-phase faults. It is easy to form a characteristic in IED. To do this, you just need to enter the coordinates of 4 points in the impedance plane, which will limit the characteristic of the zone. I'm adding a calculator. Since only the phase loop needs to be calculated, the zero sequence current compensation coefficient is not used. But I want to draw your attention to the fact that in HARTRON devices, it is a real number. Now I'll link the channels of the comtrade file and the calculator. On the first line, there is a short circuit in the first zone. The settings on the 2 lines are the same. Let's see what happens on the second line. Also, the first zone. Let's look at the oscillogram from substation B. Here is approximately the same for analog channels. But a high-frequency signal is also recorded along the lines. For the second line, there is a typical signal for the operation of phase differential protection for a short circuit on the protected object. On this side, the trip was longer, and this can be seen from the nature of the current. After the trip from substation A, the current increased. The longer trip time is due to the fact that at substation B there are older switches dating back to the times of the USSR. Let's look at how the devices saw what was happening. Let's start with the second line. Sorry, I forgot to select the loop for the calculator. There is a short circuit on the edge of the second zone, but the second zone has an operating time of 0.8 seconds. Let me remind you that this line was tripped from the phase differential protection function. Let's see what happened on the first line. It's the same picture. The impedance vector entered the second zone, but for insufficient time. How I see the course of events. A short circuit occurred between phase B of the first line and phase A of the second line without ground. On the substation A side, the shutdown occurred within approximately 80 milliseconds. Then the short circuit was fed from substation B. After approximately 160 milliseconds, the second line at substation B was disconnected from the phase differential protection function. And after that, the conditions for the trip of protection at substation B along the first line disappeared. No damage was found on these lines, and after a few hours, they were successfully put back into operation. Peace for everyone. Bye.